All right, so we will be talking about ionic compounds involving metals, non-metals, or we'll think about metal transferring electrons to non-metals. But before we really start putting metals and non-metals or positives and negatives together, we really must understand what ions are. So let's go ahead and take a look at what monatomic and what polyatomic ions are here. All right, so looking at calcium, we can start to think, we've always been thinking about the neutral calcium. So if we're going to do, guys, the electron configuration for the neutral calcium, that's fine. We first need to figure out, well, in a neutral calcium, we look at the atomic number, that's 20 protons, and there is 20 electrons if it's if it's neutral. So I'm just going to use the shorthand noble gas configuration for calcium. So we're going to do argon, that's the noble gas right before it, and then we're going to do 4s2, okay? Now, starting with the electron configuration for calcium, I want to know what is calcium going to most likely do to fulfill its octet rule. So elements will either lose or gain electrons to get to the nearest noble gas. So if you look, the number of valence electrons that we have here is 2. Okay, so to get a full octet, we can either gain 6 electrons to get a full shell, or we can lose 2. So it's much easier to lose 2 electrons than it is to gain 6. So when calcium, neutral calcium, loses those 2 electrons in its 4s2 orbital, the electron configuration would be just argon. Notice how it is positive 2, because when you when you lose 2 electrons, you lose negativity, you become more positive. That's why it's plus 2. Okay, now we're not saying that calcium plus 2 is argon, right? Because calcium still has its 20 protons, but now it has only 18 electrons, which looks to be the same electron configuration as argon. So don't confuse those two, okay? So in that case, since we lost 2 electrons to look like the nearest noble gas, argon, in our electron configuration, we have a plus 2 charge. This is called a cation. Remember, the T is for positive, okay? Now, in order to determine if sulfur will gain or lose electrons, let's first write the electron configuration for sulfur, neutral sulfur. So looking at the periodic table, it looks like sulfur has 16 protons and 16 electrons to balance that out. So let's do the noble gas shorthand configuration for that. Neon is the noble gas right before it, and then we go 3s2 and then 3p4. Okay, so on our third shell here, we have 6 total electrons. So the question becomes, okay, to get to a full octet, okay, in my valence shell, I can either gain 2 electrons to get to 8, or I can knock all these out, all these 6. So which is it easier to do, guys, to gain 2 electrons or knock out 6? Okay, so think about that for a second. All right, hopefully you thought it would be best to gain 2 electrons. Okay, so I'm going to show you how that works. So you still got neon, and then here's 3s2. If I gain 2 electrons, this becomes 3p6. So do you see how that's 2 and 6? That makes 8. Now, what noble gas is this equal to, it's not neon, that's the noble gas right before it. When I fill the third shell, the s and p orbitals, it should be, oops, I should put, because I gained 2 electrons, I should do that. And this should be actually argon here. So do you see how that works? It looks like if you look on the periodic table, argon is a lot closer to sulfur than neon is. So sulfur is going to gain 2 electrons to get to argon. So notice how I put the -2 charge. And this makes this an anion because sulfur likes to gain electrons to get to the nearest noble gas. Now, what we can say, if you can see the pattern, calcium here was a metal. And you notice that metals will tend to form a positive charge by losing electrons. Sulfur was a non-metal. So non-metals tend to form a negative charge because gaining electrons is a little bit easier for them to get to the nearest noble gas that comes next. Okay? So when we put these metals with non-metals, okay, elements that lose an electron and those that gain electrons will react by a transfer of electrons. Remember, covalent bonds are all about sharing of electrons, whereas ionic bonds are all about one electron is lost and the other is gained. Usually the metal loses the electrons, the non-metal completely gains the electron. Okay? And when these metals and non-metals get together, the resulting product will be electrically neutral, and therefore it is called an ionic compound. So I want you to think for a second. Do you think, looking at this example here, here's chlorine gas. You probably do not want to ingest chlorine gas. It's actually very toxic. Here is sodium metal, okay? I imagine just looking at that, that doesn't look very good to eat, does it now? Okay, so what's really awesome is when sodium gives up its electron to chlorine, NaCl is formed, and this is table salt. We can totally eat table salt because we need the sodium cation and the chloride anion, okay, in our diet. So what can you say about the properties of compounds? Do you think the properties of the compound that forms sodium chloride is has average characteristics of the constituent elements? What do you think, true or false? I'll give you a second. So hopefully you said that's false. Reason being is salt has completely different properties. Look, here this was a gas, this was a solid metal. Together it looks like this crystalline structure. So actually when ionic compounds are formed, the properties of the compound completely differ from the constituent elements that made up that compound. Completely different. All right, so here's a picture of what we were just talking about. When you take a sodium and you've got 1 electron, it will lose that electron and give it to chlorine. In the process, you see how this becomes 3s0? We're just showing, that the electron was lost from there, and this becomes 3p6. So this picked up a positive charge because it lost an electron. This picked up a negative charge because it gained that electron. Now, once you form ions, opposites attract, right? So these are called electrostatic forces, where the positive is attracted to the negative, and you can see we form a nice crystal lattice structure of positive negative. These tend to occur in a 1-to-1 ratio because this is +1 and this is -1. So even though you have kajillions of these atoms in a speck of salt, okay, in a crystal of salt, it doesn't matter because they're in a 1-to-1 ratio. for every 1,000 sodium ions, there's 1,000 chloride ions, okay? So we will talk a little bit more about these, but these tend to be soluble in water, but we will do solubility rules later. And once an ionic solid is dissolved in water, these ions are free again. So if you look at salt in your salt shaker, it's a solid, meaning that it looks like this. It's bonded together. But if you add that to water and salt is soluble in water, you will actually get this to break up into cation and anion, okay? And because these are charged particles, electricity is literally defined as the flow of electrons. So these compounds tend to conduct electricity. All right, so let's look at the overarching patterns here for main group elements, guys. 1A through 8A. You can predict the charge of the element based on its position on the periodic table, okay? And I want you to notice a pattern. Here's our steps or our zigzag line for the metalloids, if you remember, okay? Anything to the left of that line is a metal, okay? With the exception of hydrogen, okay, which is a non-metal. But what do you notice? It turns out that all these look positive, do they not? So if they're positive, then we can say they are losing electrons. So metals tend to lose electrons to become positively charged, okay? And these would then be defined as cations. Now, if you look to the right of the zigzag line where we have the nonmetals, those guys tend to be gain electrons to get to the nearest noble gas to become negatively charged, and therefore they are anions. So let's look at some patterns to help you see this, okay? So if you look at group 1A and 2A, they have a charge of +1 and +2, okay? Because lithium can lose 1 electron here to get to the noble gas right before it, which happens to be helium over here. So if lithium lost 1 electron, it'll have 2 electrons and looks like helium, okay? If it were to go in the forward direction, let me fill that in, and try to get to neon, that means neon is number 10, lithium is 3. It means it has to gain 7 electrons. Neon is way too far from it, so lithium will tend to lose, not gain electrons, okay? Beryllium, same thing. Do you notice how group 2A elements all have a +2 charge? Reason being is, again, beryllium has 2 options. It can gain 6 electrons to look like neon, or the other option would be to lose 2 electrons from 4 to 2 to look like helium. Who's closer? It looks like helium is closer, so of course the metals tend to lose so they can look like the same electron configuration as the one before, okay? Now, on the other hand, let's look at fluorine and anything in group 7A. All right, in this case, who's closer, neon or helium? Absolutely. So it looks like neon is closer. So if fluorine gains 1 more electron, it will have the same electron configuration as neon and will have a full octet, and so is happy that way. Okay, so halogens are very reactive for that reason. They just need 1 more electron to get to the noble gas configuration. So if we look at oxygen, is it easier to get to neon or to go backwards to helium? If it went to neon, that's 1, 2, okay? Meaning that it gained 2 electrons, so it'll be negative, okay? If it goes back to helium, then it would have to lose 6. It's way easier to gain 2 than it is to lose 6. Now, here's a curveball that isn't shown on here. What if you have nitrogen? And I know, nitrogen typically forms covalent bonds, but it does also form an ion, okay? So what do you guys think? What do you think the charge of nitrogen would be if it were to form an ion? So you're going to have to ask yourself, is it closer to neon or going backwards to helium? So if it was going to neon, it would have to gain 1, 2, 3. If it goes back to helium, it'll be 1, 2, 3, 4, and one more loop to 5 going back to helium. So in that case, it looks like nitrogen is closer to neon. Therefore, this would be a -3 charge. Okay? So all 5A elements, if they were to form a charge, they will also form a -3 charge. Notice aluminum, guys. Why is aluminum +3? Okay, do you guys see how it's to the left of the zigzag line? Because it is to the left of the zigzag line, you should automatically in your head think, hey, that must be positive. Okay, and same idea here. So if aluminum were to gain electrons to get to, in this case, argon here, it'll be 1, 2, 3, 4, 5. Argon is way too far from it. But if helium, or aluminum, sorry, gained or lost 3 electrons to get to neon, that's 1, 2, and 3, then it would look like neon. So isn't it better to lose 3 than to gain 5? Because of that, this will also be +3. So group metals, main group metals, 1A is +1, 2A is +2, 3A is +3. Now, carbon here sits right in the middle. So that is actually won't form very much ionic bonds because it can go either way. It's 4 away from neon and 4 away from helium. So it's sitting right in the middle. It probably won't form ions, okay? Now, the non-metals tend to be negative. So notice the pattern. Take the group number -8, and that will give you the charge for 5A. 6 minus 8 is -2. So group 6A elements will have a -2 charge. Now, 7A, do 7 minus 8, that's -1. So everything here will be -1. Okay, so that's -2, that's -3, and this here is -1. Notice the noble gases do not form charges because they already have a full octet. So that's why they're relatively unreactive. The other last thing that I really want you to think about is I've been talking about only main groups and using the periodic table to determine their charges. But look at these transitions. I didn't mention those. And those are the complicated case. Here, now, of course, this is an incomplete table, but look at chromium has 2 charges. Iron can come in 2 charges. Copper actually comes in copper +1 and +2. So these are the transition metals. Transition metals will form more than one ion, and there is no clear-cut pathway based on the group number to determine that charge. Okay, in addition, there is more down here. So let me see if I can fill those in for you guys here. So like gallium, and then we've got 32 here is germanium, arsenic, and then tin. So I want you to look at tin and lead down here. I'm just going to draw them. If you look at a full periodic table, you can see them. So tin and lead, are those metals or non-metals? Hopefully you answered metals because they come to the left of the zigzag line, okay? So they're metals. So they should be forming charges, okay? And particularly they should be forming positive charges. Although the transition metal line is right here, okay? And these are main groups, but they are main group metals, and they will form more than one charge. So here's what I want you to remember. So do your zigzag line. From your zigzag line to this line, okay? Anything in here, okay? If you are going to guess, you're going to guess that this will form more than one charge, okay? And we'll see how that's significant in a little bit. All right, so let's do some examples. So cesium, guys, okay, don't look at the previous slide that I gave you. Look at a periodic table, the same one that you would have on the test. Okay, so cesium here is in group 1A. It's a metal, so you're going to guess its charge is going to be positive. And because it's in group 1A, it's going to be positive 1. So it's written as +1 here. Okay, selenite is, let's see, where is that guy? So it's number 34. It is in group 6A. So you're going to say this is a non-metal. So your guess is that it should be a negative charge. Now the objective is it -1, -2, -3? So because it's a non-metal, we'll just do 6 minus 8, and that is a -2 charge. So this is Se -2 right there. Iodine is group 7A. It's a non-metal. So if I were going to guess, that is totally going to be a negative charge. There's no way it could be positive because non-metals tend to gain electrons. So we're going to do 7 minus 8. That is a -1 charge. So that's how you would write that. Of course, sorry, you didn't need to write the positive one. You just do positive or negative. The 1 is implied. Now, phosphorus is in group 5A, and it is a non-metal. So again, because it's a non-metal, I am totally going to guess that it's a negative charge. So I'm going to do 5 minus 8. That would be -3. So this is P -3. Gallium is in group 3A. And because it is to the left of the zigzag line, it is a metal. And so main group metals will have the same charge as their group numbers. So this is +3. So if it were to form a charge, it'll be +3. Hope that worked out for you. All right, so now we know how to predict where we can, for main group elements, we can predict the charge of the elements based on their position on the periodic table. Now we want to learn to name them. So when you're dealing with cations that belong to 1A, 2A, and 3A, you want to identify the metal followed by the word ion. And we'll do a few examples in a bit. Okay, so if you're dealing, guys, with transition metals that form more than one type of cation, there's two systems used. I hardly use the old system, but Mastering has it in there if you're using that platform. So you might come across it. Usually what they'll do is they'll assign the us ending to the element with a lesser charge and the ik ending to the element with a greater charge. You're in my class, I do not use that system. I totally like the new system because it is way more straightforward and it uses a Roman numeral in parentheses after the name. And I'll show you again some examples in a second. As far as anions go, so this is all for cations, okay? This is just particular for ones that form one type of charge. These are the rules for metals that form more than one type of charge. For anions, which tend to be nonmetals, we're going to change the "ine" to the "ide" ending, followed by the word ion. Okay, so let's, now there's the theory, let's do some examples. Okay, so if you're looking at cesium here, notice this is not neutral, it is an ion, so I have to say it. So I just say the name of the actual neutral element. But if I just say cesium, you're going to be thinking I'm talking about the neutral one. So you need to put a space and you need to put ion there. So cesium ion, if I just say cesium, I'm referring to just CS neutral. So be very careful with that. You need to communicate properly. So you don't want to do that. Okay, now look at selenide. Here, what we have is it's a -2 charge. Okay, so let's see. Looking at it. And so if you look at that, and I needed to just get you to make sure you understand this. So if you look at it and you were talking about just this, guys, is selenium. If I say selenium, I am referring just to the neutral selenium atom. But remember, I'm going to change the ending to an "ide" ending. So I'm going to say this is the selenide. See, selenide. We're changing this and putting the "ide" ending and putting ion. And this can be tricky sometimes with the spelling. So you got to be really, really careful. Now, if we're looking at, see how the cation, I left it exactly the same and just added the word ion. But for the anion, I changed the "ine" or whatever ending to the "ide" ending. Okay? So let's look at iodine here. If you write iodine, see how it's got the "ine" ending? And because it is negative charge, if I just say iodine, you're going to be thinking iodine neutral. But that's not what I'm saying here. I'm saying iodine with a negative charge. So this is called the iodide. We drop the "ine" and add the "ide" ending, iodide ion. Okay, now if I say phosphorus, okay, then what we're looking at, guys, is the phosphorus ion here. This is the phosphorus, elemental phosphorus. This is just neutral P. But is this neutral? It's not, isn't it? So you've got to communicate with me properly. So here, we're going to change the "urus" ending, okay? And see what I mean? You just have to practice, okay? And we're going to say phosphide ion, okay? Now, looking at gallium, look, that's a positive charge, which means I'm not going to change the "ine" to the "ide. It's just going to be gallium ion. And there's a space there, just making certain. Now, in terms of copper, if I just say copper, you're thinking neutral copper, but this is an ion. So I got to be clear about that and tell you what it is. Now, here's a curveball. If I just say copper ion, is this good enough? You may be like, yeah, why not? You know, that's what you did for A through E, right? But if you guys look A through E and you look at their location, that's what I was momentarily doing just to make certain on my periodic table, as I was looking at their location to make certain that they were main group elements. Okay, so these are main groups. They don't form more than one charge. If you look at gallium, it's a main group element, and so it'll always have a +3 charge. Okay, now if you look at copper is a transition metal, and copper comes in more than one charge, so you have to be clear about it. And that's what I mean by the new system. So the new, in the old days, they would call it cuprous ion, okay, because it is the one with a lesser charge. Again, I don't use that. I'll say copper 1, and you just need to put a Roman numeral. Now you may ask me, why did I not need to indicate the charge? Why is it okay to just put the 1 as a Roman numeral? Well, remember, metals will never be negative anyway. So therefore, you don't need to tell me it's positive. I mean, there's no way it could be -1 anyway. So copper 1 space ion. Okay, now looking at lead. Lead, you're like, well, you know, that one is in the main groups. But if you're looking at the main groups and to the left side of the periodic table besides aluminum. Aluminum will always have, like in gallium, these guys will always have a +3 charge. But you can see kind of towards the lower side. So significantly, I would circle lead, Pb, and tin as a reminder that even though those are main groups, they have more than one charge. And those are the ones that students always tend to forget about because they're not really transitions, but they do form more than one charge. Yeah, I know. Chemistry is like, there's always exceptions, right? So when you do lead, okay, here you need to do lead, no space, Roman numeral 2, space, ion. Okay, you see how that works? Again, just remember that lead and tin form more than one charge and need Roman numerals. Even if they are not transition elements. Very key point there. Okay, so that is all right. So those guys, what we've been talking about so far, were what we call monoatomic ions. Okay, because it was copper. See, it was one ion, or magnesium, whatever. That's monoatomic. We can have polyatomic ions, and these are composed of more than one atom. They're held together by covalent bonds but have an overall charge. So polyatomic ion is charged because it contains a total number of electrons that's different from the total number of protons in the combined atoms. So they are encountered so frequently that you must memorize their names. And here's one to get you started with. There's a ton more out there, but this is what I'm using for your class, okay? So it may seem a bit overwhelming, okay, to do this, but there is a little system that will help you get there. Let's talk about that system. So looking at, now don't get confused by oxyanions. All they mean, most polyatomics are actually have oxygen in it. Okay, so let's look at the 8 and the ite ending and the difference between them. Okay, so and then we'll add in the ide ending. So what I want you to think about, remember nitrogen, and we asked what is the charge on a nitrogen atom if it were to form an ion, and because it was in group 5a, we said that would be -3 charge. Now when naming that, this will be called the nitride ion. See the ide ending there, guys? Now the ide ending is specifically associated with a monatomic ion. Here we are dealing with polyatomic, so we will work with ite and 8 endings. Now, I only memorize the 8 endings. So looking at nitrogen, okay, here NO3, if in my mind I only think nitrate. So nitrate in my mind is NO3 negative. So because it has the 8 ending, it must be a polyatomic containing oxygen, which makes it different than the monoatomic that has the ide ending. So if I was going to ask you to do nitrite, notice nitrite with the ite ending, you're going to think to yourself, well, I know what nitrate is, and the ite ending always has one less oxygen, than the 8 ending. So if 8 has 3 oxygens, ite must have 2 oxygens. So, and the charge stays the same for both of them. So that's the nitrite series. Memorize one and everything will come to you after that. Okay? So, question, does that mean that nitrate always has 3 oxygens? No, that's not the case. Here's another example for you. I only memorize the sulfate. sulfate has a -2 charge and there's 4 oxygens. See, this is called sulfate, but it has 4 oxygens. So if I were to say, hey, can you tell me what sulfite is? What the sulfite ion is, make sure again it's ion, okay? Then you should think, hey, the 8 ending is always 1 less oxygen than the 8 ending, so it must be that. Now leave the charge exactly it is. Now, if I were to say sulfide for you guys, what must that be? The "ide" ending refers to the monatomic, so this is S-2 without the oxygen. Now, do you guys notice a pattern here? Look at sulfide forms a -2 charge, so does sulfite and sulfate. Okay, now this pattern won't always work, but it works for the most part, but not always. Because if you look at nitrogen, it's a group 5A. It had a -3, but the nitrate had -1. So this is an exception to that rule. That doesn't really work. But let's look at another one. Chlorate is the only thing that you need to memorize over here. So you think about it, guys, it's not CiO3, it's ClO3. So what we're thinking here is that you've got ClO3. Look at how it's a negative. Now, why is that a negative? Because chlorine is in group 7A. So if I were to tell you what the chloride ion would be, you would just say Cl negative. And see that, again, that rule works. It just doesn't work for nitrogen, okay? So if you know that the chlorate ending is ClO -3, the chloride must be 1 less oxygen than that. Now, the chlorate series also has hypochlorite in it also. So look at, what does hypo mean? Think about what it means when you're hypoglycemic. It means your blood sugar gets really low, right? So hypo means less. So hypo is 1 less oxygen than the ite. So it's ClO negative, but the charge stays the same. Now, going back to English class, if you remember your prefix per here, that means more. So perchlorate means 1 more oxygen than the 8 ending. So it's going to be ClO4 minus. So do you see how there's rules to kind of help you see it as a less overwhelming task? So just remember the 8 endings. So like sulfate, nitrate, chlorate, phosphate, for example, is PO4 -3. So if I tell you guys this is phosphate, notice how phosphorus is in group 5A, and it actually does abide by that rule. So phosphide would be what? Here, let's do that on the side. Phosphide is P to the -3. See how it's got that "ide" ending, and they do follow the same rules. Again, it seems to be nitride and the nitrate series are the only exception to that charge rule. Okay, but I didn't put this on your polyatomic chart. But can you make a guess? If I say, can you do phosphite ion for me? You should be able to, because the ite always has 1 less oxygen than the 8. So PO3 -3 is phosphite there. Makes sense? So there is a little bit of order to the chaos, okay? So summing up, these are some monatomic and polyatomic ions that you need for your biochemistry. They're biologically important to you. Like, I wouldn't worry about knowing their dietary source, but you should know what the calcium, iron, potassium, sodium, magnesium, chloride, and this is the bicarbonate ion and the biphosphate ion, or you can say hydrogen carbonate or hydrogen phosphate. These are important. You don't need to worry about their location, but mostly what is their function? That's something to look at. I hope this helped clear up some issues about ions. Next, we're going to really use them to put ions together to make ionic compounds and name those ionic compounds.